Hello again. Welcome to this all-important lesson all about this very, very important molecule we call water. So as we mentioned in the previous lesson, atoms come together to form compounds. Here are several examples of atoms bonded together to make compounds. There are two types of bonds that we discuss here in biology, and that's ionic bonds, you see those down below, and covalent bonds are the four we see up top. In biology, we primarily focus on covalent bonds. Most of the molecules that make up life are covalently bonded. So most of the bonds we talk about this year will be covalent bonds. Ionic bonds are generally crystals and rocks. Think about those types of things like a salt crystal. Those are ionic bonds, not found as much in life. So ionic bonds, an ionic bond forms when an anion and a cation, if you remember we talked about those two days ago, a positively charged ion and a negatively charged ion. An ionic bond is when they stick together like magnets. So we see the negative and the positive, they stick together and we have an ionic bond. Covalent bonds are a little bit more like tinker toys. You take a ball and you take a stick and you stick them together and we have our covalent bond. But very, very much more importantly than the two types of bonds are water. So water is this amazing compound that is kind of between ionic and covalent bonds. And that's one of the reasons why it is so amazing, such an amazing, amazing molecule. The bonds between oxygen and hydrogen, so here we have our H2O, or water molecule. So this solid line here and this solid line here represent covalent bonds. So it is definitely a covalently bonded structure. But here's the deal with water. The electrons involved in the bond are not shared equally. Remember, electrons have a negative charge. Oxygen pulls the electrons closer to himself. So because he has the electrons closer to himself, he gets a slight negative charge. We call it partial negative charge. And the symbol there is the Greek letter delta. And it represents a partial negative charge on oxygen. It's not a full charge. It's not completely ionic. It's just partially ionic. And the opposite of true over here at hydrogen. He has not completely lost his electrons, but they aren't as close to him as they are to oxygen. That gives him a slightly positive charge, a partial positive charge. And again, we symbolize that with a delta positive. Because we have this difference in polarity, a negative end and a positive end, we call that a polar bond. This is polarity. Polarity leads to a very special type of bond that we call hydrogen bonds. That partial negative of the oxygen and partial positive of the hydrogen connect together, and that makes two molecules of water stick together. So again, we've got the covalent bond between an oxygen and a hydrogen of one water molecule, but that one water molecule is going to stick to another one because of the delta positive on the hydrogen and the delta negative on the oxygen, which is very much like how a covalent bond works. It's not as strong as a covalent bond. These are only partial charges, but it's still some properties of ionic and some properties of covalent, which is why water is such a fantastic and marvelous compound. Some of the properties that water has that allows for life are stickiness. We'll talk about adhesion and cohesion. Water has dissolvability. It can dissolve a lot of substances. We call it the universal solvent. And it has a high specific heat, which means it resists changes in temperature. Again, all of these properties make it fair to say that without water, life on Earth, or at least life as we know it, would not exist. Now let's take a look at the stickiness of water. So due to those hydrogen bonds between water molecules, water tends to stick to other molecules of water. So what the picture here is, we have these molecules of water and they stick together. they also tend to stick to other polar substances. So when water sticks to itself, we call it cohesion. And again, that's the picture we see here, water molecules sticking to one another, and that causes surface tension. That's what allows bugs to walk on water. If you've ever seen a bug walking on water, that's due to the water surface tension, which is due to the cohesion, two water molecules sticking together to form hydrogen bonds. Adhesion is when water molecules bond to other substances, usually polar substances. If you remember the meniscus from when you measure water, when you put water into a test tube or a graduated cylinder, you have kind of a downward bend. That meniscus is due to adhesion. The water molecules, we're taking a look at the molecular level of the glass and the water here. Here's our water molecule, the red oxygen and the white hydrogens. And you can see they're sticking to the sides of the test tube. Here, these red and black molecules are the glass. And the water molecule is sticking to the glass. That's adhesion, and that's what causes the meniscus when you put water into a test tube or a graduated cylinder. The edges of the water are going to rise up as they connect with the sides of the glass. So cohesion and adhesion together allow for what we call capillary action, whereas water is stronger than gravity with capillary action. We see an example here of capillary action occurring. We've got some blue water, some yellow water, water dyed blue, water dyed yellow. And if you put a paper towel bridging this cup with that cup and into an empty cup, capillary action, water will climb up the paper towel out of one glass and into the empty one, and we can see the mixture of the blue and yellow water through capillary action. This is a cool video here as well. I don't know that I have time to show it to you, but if you would like, you can click on it. You can see a rainbow forming, again, through capillary action. It's a cool use of capillary action. I think a lot cooler than the science experiments we do are plants. If you've ever thought about plants, they defy gravity. Animals, we generally don't. Our mouths are at the top of our body. When we drink water, we have water go down with the force of gravity. But plants, they defy gravity. They use the roots at the bottom of the plant to bring water all the way up to the top of the plant where the leaves are. They do this through capillary action, which is both cohesion, water molecules bonding to one another, and adhesion. So we're looking at a zoomed in picture of cells of the plant, and the water molecules are sticking to one another, and at the same time, they're sticking to the wall of the plant cell. And the plants are able to move water up against gravity with capillary action, which is both adhesion and cohesion occurring at the same time. Oops, that video wants to play. Again, you can feel free to watch it on your own time. I'm not sure if we have time for it today. All right, water is also known as the universal solvent. So due to that polarity of water, again, that's the delta positive end and the partial negative end, water dissolves other polar substances. What is dissolving? Well, you're looking at a picture of it right here. Here's a salt crystal. If you ever put salt into water, it's got the positive and negative ionic bonds, and the water molecules will come over and will pull apart the negatives and the positives. Remember, the delta negative end is on an oxygen. So the oxygen ends will pull away the positives. The delta positive end is on the hydrogen. So the hydrogen will pull away the negatives. So we've probably got, again, this negatives moving away down below. We've probably got hydrogen molecules pulling those off. And up top, we see the positive ion being pulled away. That's probably the oxygen pulling those away. So water dissolves a lot of substances, even rocks. I mean, think about a salt crystal if it's not dissolved. That's almost like a rock. Water dissolves it, pulls it apart, makes it so that you can't even see the rock. Quite a cool thing. So for this reason, we call water the universal solvent. But just as importantly as what water will dissolve are the things water won't dissolve. For instance, oil. If you've ever poured oil into water, it doesn't mix. Water will not dissolve oil or other nonpolar substances. And that'll be really important as we progress through biology. Water does dissolve polar substances or charged substances. It does not dissolve nonpolar substances such as oil. We actually have special terms for this. Substances that mix with water are called hydrophilic. So it's a Greek word, hydro for water, philic for loving. And substances that don't mix with water, like our oil in this picture here, are called hydrophobic. Again, a Greek word, water fearing. So hydrophilic and hydrophobic. Two terms, you'll hear it again. So water dissolves so many things that we actually have a whole classification system for how things behave when they're in water: acids and bases. Acids are generally defined as something that when you add to water, you increase the hydrogen ion, that's H plus, concentration. So here's a substance, it goes into water, and H plus comes off. That makes it an acid. Bases are generally defined as when they dissolve, OH negative, called the hydroxide ion, comes off. So here we have an object. When it's gone into water, a hydroxide ion comes off, and that makes this a base. Finally, last property of water we'll talk about is the high specific heat. So specific heat is a measure of how easily something changes temperatures. Water has a very high specific heat, which means it takes a lot of energy to warm water up. And vice versa, once water is warmed up, it loses its temperature very slowly. So as an example, let's say we have 1 pound of metal and 1 pound of water. If they're at the same initial temperature, so let's say they're both at 0 degrees Celsius, and we apply the same amount of heat for the same amount of time, we're going to end up with a hot piece of metal. That metals generally have a very low specific heat. It doesn't take very much energy to warm up metal. Water, on the other hand, high specific heat, takes a lot of energy to warm up the water. So it's not going to be hot to the touch. The metal is now hot to the touch. The water, not so much. It's able to absorb a lot of heat because it has a high specific heat. Hey, we learned quite a few terms today. If you're looking at this slide and any of these sound unfamiliar, it might be worth it to you to go back and watch the video again so that you're more familiar with some of these terms. Similarly, here are some questions you should be able to answer after having watched this video. If you're reading any of these questions and you aren't sure what the answer is, it might be worth it to go back and rewatch the video and pay more attention to what some of these questions are. That does it for our lesson on water. We'll see you tomorrow.